Thank you, Jesus. So first of all, I would like to thank Jesus and Ricardo and the rest of organizers for inviting me to give this series of 2 talks, and especially for organizing a conference in Badajoz. It is always a pleasure to come to Extremadura to study Banach Spaces. I think I was talking with Ricardo a few minutes ago that this is 18 years ago, last time I came to Extremadura, so really a lot. We had, probably the same hair, but a little bit more black. Okay, so my idea in this series of talks is to first give a somehow survey of classical results on non-attaining linear operator. There will be not multilinear, nor polynomial, nothing of this kind, only bounded linear operator in this talk, and there will be nothing related to this new Bischoff-Feld-Bolovaz or local property or whatever, only the, let's say, classical theory. Then first I will give an overview of classical in the sense that they are before 2014, I guess, and then I will give briefly three new topics in the sense that they are newer than 2020. Okay, so the plan, this one. Oh, no. We have the, oh, no. Okay, so, working. Well, the roadmap of the talk will be this, of the 2 talks. First, the preliminaries, then this overview on classical results, and then the 3 topics will be the relation with the RMP and the range space, and property A and the residuality of non-attaining things, and finally, we will talk about final rank operator. No. Okay, let's go with section 1. I don't know whether to take the keyboard and work with the keyboard, because this is almost impossible. Okay.
There's no whiteboard there.
Sorry? No way. No way. Is the program is not working? It's not the. Oh, now, but well, life in Badajoz is relaxing, so computer do the same. Oh, for the volume is working. Okay, so let me see whether I can follow. This will be the notation, everything very usual, just the unit ball, the unit sphere, the bounded linear operator, weakly compact linear operator, compact linear operator, and finite rank linear operator. And we will write X star for the topological dual of X. And this is the usual relation between finite rank, compact, weakly compact, and operator. Nothing complicated to follow. Okay, the recent result part will be mainly based on this paper. This paper in Praxan with Hensu Choi, Jung-San Choi, and Minggu Jung. This paper in Junio Mathematical Analysis and Application with Hensu Choi, Minggu Jung, and Sun Kwon Kim. This paper in the Junio Functional Analysis with Minggu Jung and Abraham Rueda. And finally, a chapter in the book dedicated to Victor Lomonosov, what is called non-attaining operator finite rank, with Vladimir Kade, Ginel Lopez, and Dirk Werner. Okay, so the problem is it's going to be in a Badajoz way, relaxing. So what is a non-attaining functional? It's just a function with a functional which attain the norm. Functional mean linear and bounded here, and attain the norm means that there is a point so that the supremum defining the norm is just a maximum at this point. And we will write NAXK for the set of non-attaining functional. Some example, well, in the finite dimensional case, of course, every functional is non-attaining. If X is reflexive, the same is true. This is just Banach. And the reverse result is also true. This is James' theorem. In C0, the non-attaining functional are just those sequence in L1 which has finitely many non-zero elements. Or in L1 are the sequence in L infinity such that the L infinity norm is actually a maximum. But this set can be wild. For instance, it may contain no two-dimensional subspaces. This has been very recently proved by, or somehow recently proved, by Remutil using an example of Charles Reed. And it can be even not Borel. So complicated, topologically complicated. Why it can be interesting, the set of non-retaining functional? For instance, there is a classical result by Bethune-Plisco, which was rediscovered by Godefroy, that if you have a separable, a Banach space with this separable, and you have a subspace of this dual with this subspace, and is closed, containing in the set of non-retaining functional and separating point, then automatically it's a pre-dual, isometrically. Okay, and what is a non-retaining operator? Well, the definition of a non-retaining functional, pass to operator, just considering function with linear function with go to y, and the non again is a supremum. When the supremum is a maximum, then you get a non-retaining operator. The notation NAXY is the set of non-retaining operator. Some example, if the dimension of X is finite, again, every operator is non-retaining. This is, again, Heine-Borel. But if the dimension of the domain is infinite, then you can always find an operator which doesn't attain the norm. This is not complicated. If X is reflexive, compact operators are contained in the set of non-retaining operators for every y. In the case of the domain spaces L1 or the range spaces L infinity, it is easy to describe both the space of operators and which operators are non-retaining. Are exactly the same that you can get thinking in that they were functional instead of operator. This is exactly the same result. Okay, but for instance, it is not clear what is the set of non-retaining operators from L101 to L infinity 01. Probably it's easy to find, to construct one, but not to construct many. It is really hard to find which operators are here and which operators are not here. Okay, so the problem of non-retaining, of denseness of non-retaining functional and operator, the first problem was very old, whether the set of non-retaining functional is dense always in X star. If X is reflexive, then this is total. It's the Gould dual. Then at the very beginning, they call sub-reflexive for those spaces such that this is dense. And then Bischoff and Feld proved that every complete space, every Banach space, is sub-reflexive. So this is then for every Banach space. What about operator? Well, 2 years after the paper by Bischoff and Feld, Lindenstrau studied this question and answer negatively the problem. There are operators between Banach spaces, bond-linear operator between Banach spaces, which cannot be approximated in known by non-retaining operator. Okay, so let's start with this overview. So first, Lindenstrau result, the relation with the RMP, this, when Bourgain come into play, many counterexamples for property B, a few of results on classical spaces, and a little bit of compact operator. Okay, so for this overview, the bibliography can be these 3 items, 2 papers in Lancien. The first one is just a survey. The last one is not exactly a survey because it's a survey plus a lot of new results. And in the middle, you can find a master thesis, what was written by a former student called Angela Capel, not in my university, but was my student, and can be found online easily. Okay, so what Lindenstrau did in this seminal paper? First, that it is not always dense. And why is not always dense? Well, the idea is very simple, is that if you have a monomorphism attaining the norm, and the image is locally uniformly rotan, then automatically the point where the operator attains the norm has to be strongly exposed. Why? Because the locally uniformly rotan, actually you don't need that much that locally uniformly rotan. If the image of the point where I attain the norm is a strongly exposed point, then this goes back. Of course, you use D as the monomorphism. What you get with this? Of course, if you have a Banach space with this, I put separable, because this is separable admit a locally uniformly rotan renorming, and has no exposed point, like C0, C01, L101, then the identity is a monomorphism. I mean, from this X to a locally uniformly rotan, is a monomorphism that cannot attain the norm. Okay, this doesn't mean that it cannot be approximated, but the set of monomorphism is open, and no monomorphism can attain the norm. So you have an open set where you cannot go. So it is non-empty, the set is not dense. Okay, another result by Lindenstraub with this usually is people say that this is the first negative result, but it's not, because if you consider in a paper that something with this in page 2 is earlier than something with this in page 4, then the earlier result is the first one. But anyway, it is rather easy, and I will more or less give a sketch of the proof to prove that if you have a operator from C0 to a strictly convex space, which is non-attaining, then automatically it's finite rank. And this is because C0 has a very, very, very big phases. Okay, then this gives, again, that if you renome C0 strictly convex, or you have a strictly convex space which contains C0, then the set of non-attaining operator from X to Y, or from C0 to Y is not dense in L of C0Y. Okay, so the question is for which X and Y the density hold. Well, as the problem is too general, Lindenstraub introduced two properties. One is property A, meaning that you have an operator X with this valid always as a domain, or property B, when you have a Banach space Y with this always good for density as a range space. Okay, and the first example is the finite dimensional space has property A, the base field has property B, this is Bischoff fell, C0, C01, L101 fail property A, and if Y is strictly convex and contains C0, then it's fail property B. Okay, positive result. Well, let me, well, sorry. Lindenstraub proved that the set of B transpose of the set of operators whose B transpose attain the norm is always then in the set of operators from X to Y, no matter X of Y. And not only that, that you can perturb using a compact operator. Okay, this gives that if X is reflexive, then automatically has property A, and then this is if this is reflexive, it has property A in every norm, because in every norm is reflexive. Let me say that the property A, property B, or the density of non-attaining operator depend on the concrete norm that you have in X and you have in Y. Changing the norm, then you change the possible density or not. Okay, this let improve the result, proving that you only need to take that joint one time. Okay, more positive result. Well, using these ideas, you get that property, Banach spaces with property A are, for instance, L1 and finite dimensional, all finite dimensional spaces. But for property B, there is other result of Lindenstraub that I didn't mention before, that every subspace of L infinity containing the canonical copy of C0 has property B. But if you want a finite dimensional space to have property B, at the time of Lindenstraub, it was only known that polyhedral finite dimensional spaces have property B. But only a little bit is known. Now it's only a little bit more is known. Okay, so positive result up to renorming is that every Banach space can be renowned to have property B, and separable Banach space can be renowned to have property A. So it's really a property we depend. So, but we can live in the world of separable Banach spaces, and it's not a problem for this talk. So every Banach space can be renowned to have A and B. Okay, so they depend on the concrete norm. Okay, so what is the relation with the Radon-Nikodym property? Well, a Banach space has the Radon-Nikodym property if the Radon-Nikodym theorem is valid for X value vector measure. But there is a geometrical characterization of the Radon-Nikodym property in terms of dentability. A subset is called dentable if it contains slices, so intersection with half space, of arbitrary small diameter. And a subset is called an RMP set if every subset has this property. And it was proved in the 70s, with the work of many people, that it's the same that X, the Banach space has the RMP, so that's something related to vector measure, or the unit ball is an RMP set, so something related to the set, the size of the slices of the subset of the unit ball, or bonded set. But if you go to the monograph by Joe Diesel and Jerry Uhl, vector measure, there are more than 30 different reformulations of the RMP. Some of them are writing intent of the non-attaining operator. Okay? Okay, so what is the main result of the relation of the RMP and non-attaining operator? Is that Bourgain proved that the RMP implies property A. But he proved even more. He proved that instead of thinking of an operator with the supremum known on the ball, you can think of an operator with the supremum on every subset, no matter. You get the same. And then you can say that data in the known, if the supremum giving you this known or semi-known, is actually a maximum. Okay, Bourgain proved that this can be done in every subset with this absolutely convex, closed, and bounded. Actually, Bourgain and Stigall proved what is called somehow non-linear Bourgain-Stigall variation of principle. The name is looked not to be, Stigall is not very happy with the name, but what can we do? That you can do this not only for bounded linear operator, but for a very large class of functions. Okay. So the negative result relating to the RMP and property A is the converse. Bourgain proved that if you have a separable, bounded, closed, and convex set that has property A for this set, so the operator attaining the known from X to any Y attaining the supremum on C, if this is dense for every Y, then automatically the set is dentable. This means that contains slices of arbitrary small diameter. In particular, if a Banach space is separable and has property A, the ball has to be dentable. Actually, Lindenstrauss has proved much more. Has proved that in this case, the unit ball is the closed convex hull of the strongly exposed point. The difference is that Lindenstrauss only worked with the given known and only worked with the unit ball. And Bourgain worked with any set. And then he was able to get a characterization with the help, somehow help of half. He proved that if you have a Banach space failing the RMP, then you get two equivalent renorming so that the identity from one to the other cannot be approached by non-attaining operator. So in particular, the set of non-attaining operator is not dense in the set of operator from X1 to X2. Okay, so this gives an isomorphic characterization that if every renorming of X has property A, then X has the Radon-Nikodym property. And for instance, L1 has property A in every equivalent norm. And on the other side, on the side of the ring space, if every renorming has property B, then X has the RMP. But what about the convex? Does the RMP of the ring space implies density of non-attaining operator, property B? Well, the answer is no, but it has to wait 2 hours. That gives an example in 1990. But to get an equivalent, it is possible. But then you have to change the definition of non-attainment to get something with this weaker, what we call quasi-non-attainment, and we will see later. Okay, so more counterexample for property B. So in the 80s, it wasn't known whether RMP implies property B. So the solution, the first solution was given by Goyo in 1990, showing that LP failed property B. But actually, Acosta proved that every infinite dimensional strictly convex space failed property B. Also that L1, little L1, failed property B. And very recently, Audrey-Fauvel proved that actually LP sum of finite dimensional spaces fail property B when P is between 1 and infinity, for P equal 1 is not known. As a consequence, if every renorming of Y has property B, then Y has to, if Y is, for instance, separable, admit an strictly convex renorming, then Y has to be finite dimensional. So a nice question is whether the converse is true. So it is true that finite dimensional space has property B. It's the same to say that every finite rank operator can be approximated by non-attaining operator, but this is not known. There are some non-polyhedral finite dimensional spaces with property B, but just some. And for instance, in dimension 2, the only known are the polyhedral one. In dimension 3, there is you can construct examples which are not polyhedral and have property B, but they are very similar to polyhedral. Okay, some classical spaces. Well, Johnson and Wolf proved that the non-attaining operator from one CK to another CK is always then in the set of operators. The same is true for operator from one L1 to another L1. Weakly compact operator acting from CK spaces always can be approximated by weakly compact operator attaining the norm. And as a consequence, non-attaining operator from CK to LP are dense for P between 1 and infinity. Well, also true for infinity because of the first result. This for L1, L infinity, also non-attaining operator from L1 to L infinity are then in the set of operator. And some negative result, operator from L101 to C01 cannot be always approximated by non-attaining operator. And C01 has not property B and was the first classical example. The other example before this one were some renorming, ad hoc renorming of some space. There's another example by Yule that if you have an strictly convex space and the non-attaining operator from L101 to this space are dense, then automatically the space has the Radon-Nikodym property. Well, compact operator. Well, it was an open question from the 70s. People were asking, and it's asked in many papers, that whether every compact operator can be approximated by non-attaining operator. It's reasonable to think about, but to think that this can be true, especially in the 70s where the approximation property was not clear. I mean, the approximation property exists, but the counterexamples for the approximation property didn't exist. So it was possible that every compact operator can be approximated by finite rank operator. So, okay, but this is not, now we know this is not the case. So the problem is that when you construct a counterexample of an operator that cannot be approximated by non-attaining operator, you always use an operator with this non-compact. Always. Before 2014. And then what happened with compact operator? And actually, in the proof, what you use is that you have an operator which is not compact, and the operator which attain the norm are finite rank or compact by some reason. And then you don't get density. In most example, it was even known that compact operators attaining the norm are dense. For instance, when X is C0, C0L, or L1 mu, or when Y is L1 mu in the real case, of Y is a pre-dual of L1, or a subspace of E0 with the approximation property, or Y is a uniform algebra, or X is a pre-dual of little L1. In all these cases, you have density of compact operator attaining the norm. But the solution to the problem is not. There are compact operators which cannot be approximated by non-attaining one. And how this can be done? It is rather easy, the example. So let me just show you in a few minutes. The first result, say, extending Lindenstraub, is that Lindenstraub proved this result for C0. Lindenstraub proved that when X is C0, X is C0, and Y is strictly convex, then every non-attaining operator has to be of finite rank. But the idea of Lindenstraub can be easily passed not only to C0, but to subspaces of C0. And the idea, what I try to draw here, is that C0 is asymptotically flat, meaning that when you have every point of the unit sphere of C0 is not an extreme point. But it not only is not an extreme point, it has a hue phase when the point is in the middle. Hue in the sense that it's finite codimension. But if you send this point to a point with this strictly convex, with this an extreme point, then the Gould phase has to go to the same point. But if the Gould phase is something with this finite codimension, then you are saying that your operator sent a finite codimensional subspace to 0. So your operator is of finite rank. Okay, then Enflo came and proved that not every Banach space has the approximation property. What does this mean? That there is a compact operator that cannot be approximated by finite rank operator. But you can suppose that your operator which cannot be approximated is the domain is a subspace of C0. And you can suppose, if you want, that the range is C0 with an strictly convex norm. So there is a compact operator from a subspace of C0 into C0 with a strictly convex norm that cannot be approximated by finite rank operator. By adding these two results, you get that compact operator cannot be approximated by non-attaining operator. Okay, actually, you can even find a subspace of C0 with Chowder basis and an operator compact which cannot be approximated by non-attaining operator. And the idea is that X has Chowder basis, but the dual has not the approximation property. X has, but X star not. But let me say something more. The basis constant of this Chowder basis is 8 and cannot be less than 2. Very crazy, but because if the basis constant were less than 2, automatically the basis were shrinking, and so the dual has the approximation property. Okay, so some interesting problem to be partially solved here in this series of talks. First is relate the RMP of the range space and the density of non-attaining operator. On the one hand, the usual non-attainment notion do not work. On the other hand, the idea should be to introduce a new notion with this weekend. Okay. Problem 2, find isometric characterization of Lindenstraub property A. Well, you can say, well, what about Bourgain characterization? Bourgain characterization is isomorphic characterization, because if you have property A in every equivalent node, then you have the RMP. But what about intrinsic characterization for the given node? You can write this property A in 10 of X and the dual, and not in 10 of the operator on every Y, which is a very strange property. Well, let's start with improving the necessary condition. Well, the first thing should be, there are necessary conditions. Are they sufficient? Not. Then we will improve the necessary condition. And we don't know whether these new necessary conditions are sufficient, but we will check if they are sufficient somewhere. This will be more clear in the next talk. More problem. Does every finite dimensional Banach space satisfy Lindenstraub property B? This is the same to say that every finite rank operator can be approximated by non-attaining operator. So at the end, can be approximated by non-attaining finite rank operator. This is not known. But let me say more. It is not clear whether you are able to find a Banach space X such that every non-attaining operator from X to L2 is of rank 1, or 0 or rank 1. And let me try just few words about why this can be interesting. How in all examples that we have before, negative example, all are of the same kind. For some reason, you prove that non-attaining operator has to be, let's say, finite rank. What you usually do is finite rank. Then either you have a compact operator which cannot be approximated by finite rank, or you have an operator which is not compact, so it cannot be approximated by finite rank operator, and then you get a contraexample. But if you want to do the same for finite rank operator, what do you do? Well, one thing, if you think the same, in every Banach space X, or in every Banach space Y, if you want, you can always find rank 1 non-attaining operator, just taking non-attaining functional. But how to construct a rank 2 non-attaining operator is not clear. So maybe the way to prove that there is a contraexample is proving that every non-attaining finite rank, or every non-attaining operator, finite rank or not, is of rank 1. This looks to be hard, but we don't know whether this is true or not. The other possibility is to say that every non-attaining operator is of rank less or equal than 23. But 23, I mean, why 23? I don't find how you can prove that. Okay, so let's go to other open problem. Which are not going to be solved, not going to be commented in this talk, more or less. Well, maybe the most famous, or one of the most famous problems of non-attaining operator is a Storky problem, whether it is possible to find an infinite dimensional X such that the non-attaining operator from X to X, or all operators are non-attaining from X to X. This is not clear, and Sheldon will talk on this, I think, tomorrow. So please attend this talk if you want more information on this.
I'm not answering questions.
This is a strange question because it looks to be complicated to be true, but we do not know of any dual space which has not property A. But this is not because we know that most dual spaces have property A. It's because we don't know if they have property A or not. Of course, if the dual is separable, it has the Radon-Nikodym property, and then it has property A. Nothing to say. But then, if you want dual and not separable, next step is L infinity. Okay, for L infinity, the problem is that the necessary condition on property A that we know is satisfied by L infinity. So we have to probably improve necessary condition, or maybe it's true, I don't know. Or you go to, let's say, James 3 space. Then James 3 space has this property. If you take, it depends on what you call James 3 or you call the dual of James 3, but usually James 3 has the Radon-Nikodym property. The dual has not. The bidual has a Radon-Nikodym property. The third dual has not. But the point is that the dual which has the Radon-Nikodym property has property A. And the dual which do not have Radon-Nikodym property satisfy the necessary condition we know for property A. So, no idea. Well, instead of little L infinity, you can put capital L infinity. Which is isomorphic to little L infinity, but it's different now and probably more complicated to get property A or not, I don't know. So problem 6 is to find necessary condition for Lindenstraub property B. We do not have, because Lindenstraub proved some necessary condition for property B in his paper, but he wrote, probably this is nothing, because probably the necessary condition we get don't use that the space has property B. And this is true. What's proved later that, for instance, every separable Banach space has the property that Lindenstraub puts as a necessary condition. So there is no necessary condition. They should be on smoothness, in the same way that the necessary condition for property A deal with rotundity or strongly exposed point or whatever, RMP, which is something related to the rotundity of the space or the convexity of the ball. Then the one for Lindenstraub property B should be on the kind of smoothness. But should be is something that I think should be. I don't know, because I don't know any property. Why not to study new classical spaces? Because when I say classical spaces, the definition of classical spaces is not clear for everyone, and it is moving in the time. In the 70s, classical spaces were CK, LP, predual of LP. This is what is considered classical spaces. But nowadays, there are more classical spaces which are very good for convex sample, like free spaces, like spaces of Ricci function or Ricci vector value Ricci function. So why not? I have no idea. Not only whether they have or not property A, property B, but even if you have operator from some Ricci free spaces to another Ricci free spaces, what you need in M1 and M2 to get density? I have no idea. Okay, so let me go to the, I will promise, I promised 3 topics. Then my idea is to cover 1 today and 2 the next day. Okay, for the first topic is the relation with the Radon-Nikodym property and the non-attainment of range space. Well, there is no symmetry between domain and range with respect to the RMP and non-attaining operator. Because if the domain has the Radon-Nikodym property, then you have density of non-attaining operator always. And if you have density of non-attaining operator always in every equivalent norm of the domain, then you get the Radon-Nikodym property. But for the range, you have, if you have this in the separable case, for instance, for all norming, or for all renorming of the range, then you have the Radon-Nikodym property. But the Radon-Nikodym property is not sufficient to get density of the range. It's not sufficient to get density of non-attaining operator. So our idea is to find something which covers this symmetry. Well, then this is a new definition of quasi non-attainment, and then we will show what is the relation with the Radon-Nikodym property. I will very briefly speak about a weaker notion of weak star quasi-Nord attainment, and finally I will present open problem in this line with some tips. Okay, so this paper is based on these two papers of the four I present. This with Henshu Choi, Jun San Choi, and Mingu Jun the first, and the second with Henshu Choi, Mingu Jun, and Sun Kwon Kim. Okay, so a weaker notion of Nord attainment. We say that an operator quasi-attain the norm, writing Q and A, if, let me see here, if you consider the closure of the image of the unit ball, then there is a vector of maximal norm. If Nord attainment means that you get the same without closure. But if you can approximate using Txn a vector of maximal norm, then we say that this operator is quasi-Nord attainment. Well, this looks very weak. This looks that every operator satisfies this property. Well, of course, rank 1 operator satisfies this property, or finite rank operator satisfies this property. Actually, compact operator satisfies this property. Why? Because an operator is compact if, and only if, the closure of TBX is compact. But if this compact has a vector of maximum norm, or maximal norm. Well, this is true. So the first remark is that, of course, Nord-attaining operators are quasi-Nord attaining. And compact operators are for free quasi-Nord attaining. Oh, yes, I forgot to say that I say that this definition is from Godefroy, but not exactly this, because Godefroy gave the definition for Lipschitz operator. But when you take the Gilles definition and restrict to bundle linear operators that are, of course, Lipschitz, then you get this definition. Okay. The first positive example, you have a pair of Banach spaces such that NAXX is dense, or every operator is compact, then automatically you get a quasi-Nord attaining operator are dense. Okay. The first negative example was given by Godefroy in his seminal paper on this topic, that if you have a renorming of C0 with the K-descript property, then quasi-Nord attaining operators from C0 to Y are not dense. Actually, it is more. It's instead of thinking on linear operator, you think on Lipschitz operator with this with analogous definition, instead of taking here the closure of the T of the unit ball, you get the set of slopes and make the closure. And this, the definition is whether this has a vector of maximal norm, Lipschitz norm. Okay. Then it is also not true that the identity from C0 to Y, which is linear, can be approximated by Lipschitz operator attaining the norm in this weak way. Okay, more negative result. Well, there is two easy remarks saying that they are completely stupid remark, but very important. Stupid in the sense that at the moment you think on them 2 seconds, they are obvious. But if you think on them by 2 seconds, then you don't see them. They were given to me by Rafael Payá, discussing this thing with him. Well, of course, I mean, this was the observation of Rafael Payá. This is even more obvious. That if you have a monomorphism, and you have an operator which cannot be approximated by Nord-attaining operator, then it cannot be approximated by quasi-Nord attaining operator. Why is so? Because if you have a monomorphism, then the image of the unit ball is a closed set. But if the image of the unit ball is a closed set, of course it's the same to have a vector of maximal norm in the set or in the closure of the set, obvious. But the important thing is that the set of monomorphism is open. So no monomorphism is on some class, cannot be approximated, then you have an open set that where you cannot get by closure. Okay, so some result of the literature showing spaces where non-attaining operators are not dense, you go to the proof, and the proof shows you that the operator that they prove that is not cannot be attaining but approximated by non-attaining operator is monomorphism. Then automatically you get these two examples. For instance, that there is a compact space S such that quasi-non-rotating operator from L101 to CS is not dense in the space of operator from L101 to CS, or just using Bourgain and Huff result, because Bourgain and Huff actually prove that you get two renorming such that the self-non-rotating operator from one to the other is not dense, but actually they prove that the identity cannot be approached. The identity is a monomorphism, so automatically it cannot be approached by quasi-non-rotating operator. Okay, so what do we get with the range space? The idea is that if you have a bounded linear operator such that the image of the closure of the image of the unit ball is an RMP set, then you can find a quasi-non-rotating operator such that it is close to your given operator and the difference is of rank 1. So it's a rank 1 perturbation of your given operator. But actually you get a little bit more. You get that this operator attains the norm in some strong way. But this strong way cannot be with respect to the point where it's attained the norm, because there is no point where you attain the norm. So it depends with respect to the image. So if you have a norming sequence in Bx such that S of xn goes to the norm, then the image of a subsequent is going to a rotation of your point which has maximal norm. So in this sense, it's strong. How it is proved? I just give the idea. The idea is to use Bourgain-Stiegel nonlinear optimization principle, but on the range space, where you have the RMP set. And then take as an RMP set T of the unit, the closure of T of the unit ball, as a function using in the function with this upper semi-continuous and bounded above is just the norm. So very easy. And just playing a little bit, you get the result. And what are the consequences? Well, if either X or Y have the Radon-Nikodym property, then quasi-non-rotating operators are dense in L of XY. The case of X needs Bourgain result, because even if X has the Radon-Nikodym property, it is not true that T of the unit ball closer is an RMP set. This is not true. But if Y has the Radon-Nikodym property, then the result is not true for linear operator and need our result. For instance, weakly compact operator can be always approximated by quasi-non-rotating weakly compact operator. Or there are many examples of pair where Q and A is dense, but the non-rotating operator is not dense. For instance, as proved by Goyo, there is a Banach space G, so that the non-rotating operator from G to LP are not dense, but LP has the Radon-Nikodym property, so quasi-non-rotating operator from X to LP is dense for every P. Characterizing the RMP, now we have symmetry. The following are equivalent. A Banach space has the Radon-Nikodym property. For every renorming of the Banach space, you get density of quasi-non-rotating operator having this renorming as domain or having this renorming as range. So now it's completely symmetric. So A, if and only B is true for non-attainment, I said before. C implies A is true for non-attainment, but A implies C is what is new. It's false for non-attainment, it's only new for quasi-non-attaining, and was shown by Goyo. Okay, we can use this set to characterize some properties. Well, it is clear that non-attaining operator is contained in the set of quasi-non-attaining operator. These are operators. And then you can discuss whether each of the inclusion is an equality. For the first one, when every operator from X to Y with this quasi-non-attaining automatically is non-attaining, this actually characterizes reflexivity of the domain. And it is true for every Y or just for one Y. Because actually, this is just James' theorem, because you can think just on rank 1 operator. If every rank 1 operator are automatically quasi-non-attainment as every finite rank. So if rank 1 operator are non-attaining, then the space is reflected by J. With respect to the other equality, well, it is rather easy to prove that if the dimension of the domain is infinite, you can find an operator from X to C0 which is not quasi-non-attainment. Maybe it can be approximated, but not quasi-non-attainment. But if the dimension of the ring is infinite, then you can always find an operator from L1 to Y with this not quasi-non-attainment. But if you think a little bit on this, what you get is the following. You get a set with this just T of the closure of T of BL1 with this absolutely convex closed inset of the unit ball of Y, such that the supremum of the element of the set is 1, but it doesn't intersect the unit sphere. This can be proved previously, but this is a new proof of this. Okay, just one transparent on weak star quasi-non-attainment. Just, okay, if you go to a dual space, why instead of taking the closure of T of Bx with the norm, why don't take the weak star closure? You get a new definition. The new definition can be interesting or not, whether it's depending on you get new result or interesting result or not. Okay, but we say that the operator is weak star quasi-non-attainment if the weak star closure of TBX has a vector of maximal norm. Okay, the notion depends on the pre-dual because depends on the weak star topology. And there is concrete example arriving to C0 star, which is L1, or C star, which is L1, depending on whether you take one weak star topology or the other. The main result is that here you cannot characterize anything because you get density always. Density in norm. You close in the weak star topology, but you get a sequence of operator attaining approaching your operator in norm. And it is not only that the Rhoen space is a dual space, because there are operators from C0 to a dual space which cannot be approximated by quasi-non-attaining operator, but can always be approximated by weak star quasi-non-attaining operator. Okay, so let me just finish with some related open problem with some tips. The first one, recall Ostrowski problem, whether there is an X infinite dimensional so that every non-attaining operator from X to S, every operator from X to S is non-attaining. Of course, you can ask the same with quasi-non-attainment. The point is the following. This problem is very hard. Why? Because if there is an example, it should be separable, reflexive, without one complementary subspace with the approximation property. Sheldon will explain better, but this is the point. So this is weak, so maybe this is easier. We don't know, anyway. But there's one remark which is interesting. Compact operators are always quasi-non-attainment, and identity is non-attainment from X to X. So what about the sum? Imagine you have an operator, you have a Banach space so that every operator is just a multiple of the identity plus a compact one. There are spaces of this kind. So why not trying this kind of spaces? The problem is that if you have an operator which is of this form, a multiple of the identity plus a compact operator, if this operator belongs to Q and A and lambda is not 0, then automatically belongs to NA. So actually you don't get much more. So it's more or less the same problem again. Okay. The second open problem is, let me introduce two properties, property quasi-A and property quasi-B, as Lindenstraus did for the non-attainment. Property quasi-A means that X quasi-non-attaining operator from X to Y are dense for every Y, and quasi-B means that quasi-non-attaining operator from X to Y are dense for every X. Okay, well, it is true that if you have this quasi-A, then you actually have Lindenstraus property A? We don't know. But for property B, it's not true, because RMP implies quasi-B, and Goyo proved that there are RMP spaces don't have property B. And I think this is all I wanted to say today. So thank you very much for everything. No, 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 no. Go ahead.
Have you studied the set of quasi-normatane?
Sorry.
Have you studied the set of quasi-normatane but not normatane? Like to know how big these sets are?
We have studied when the two sets are the same, but
Hello, hello. But I already made a question, so. So I asked if they studied how big is the set of quasi-normatane but are not normatane, if this set is big or not.
no, we didn't study. We studied when they are equal, but not how big is it.
And on empty, you showed two examples.
Yes.
Okay.
Any other question? Talking about stupid questions, could you go back to the problem of the compact?
Sorry. I'm going forward. Here?
Back.
Um,
Back, a long way back to,
Oh.
to the solution to the problem of the
To the beginning.
more.
Not the beginning, almost.
There was a moment,
Here. Yeah, here?
yeah, there.
Here?
Third line, there is a compact operator not approximable, but every operator compact with values in C0 is approximable.
Oh,
but
sorry,
then-
sorry, no, there is a mistake there.
Ah.
This is not C0. Sorry,
Ah.
there is a mistake, you're right. This is a subspace of C0.
Ah, okay.
A subspace of C0, sorry, you're completely right.
Okay.
There's a big mistake there, because C0 has the approximation property.
Yeah.
No way. But there is a subspace of C0, and the way is the following. There is a subspace of C0, that's called Y, which fails the
Yeah,
approximation property.
Yeah,
Then Remón is strictly convex and still fails the approximation property. And then there exists a compact operator to him that it cannot be approximated by finite rank.
Yeah.
And you can suppose that the domain of this operator is also a subspace of C0. Sorry, and thank you for pointing out.
Okay. Anything else? Please.
Okay, so at the beginning there were some answers about norm-attaining operators for some classical classes of spaces, right? Such that for some classes of spaces, norm-attaining is equal to all linear operators.
Oh, yes.
Are those
sorry.
questions also answered for quasi-norm-attaining operators?
No.
Okay, I see.
Whether every operator from X to X is quasi-norm-attaining?
Yes.
No, it's not answered. This is the last problem I mentioned.
Mm-hmm. Ah,
Not answer. I don't know whether the problem is easier or not. It depends on whether the solution will be yes or not. If the solution is not, it's more complicated than that obstructive problem. But if the solution is yes, if there is an example, it's easier. But we don't know. We think that it's possible there is a counterexample, but we are very, very, very far to just saying crazy thing. I mean, it can be true or not. I have no idea.
Any other question? Okay. We'll make a break. We'll meet at 11:30. Let's thank the speaker again.
First of all, I would like to thank all the organizing committee for organizing this satellite conference of the European Congress, and also for the nice invitation. Okay, so the complexity of Banach spaces that I will speak about is the Borel complexity, and it was the one that was built by Benoît Bossard in the 1990s. Okay, so the idea is quite simple. There is a space which is universal for separable Banach spaces, which is a space of continuous function on the Cantor set or on the unit interval. And the set of closed subset of C of delta can be equipped with what is called the Effroth-Borel structure, which is a sigma algebra generated by those sets, the intersection of the set of all F that intersect a given open set. And this generates a sigma algebra and it is a standard Borel space in the sense that this sigma algebra can be given by a Polish topology. So in this setting, I will call SB the set of closed subset of C of delta that are also linear subspaces, which is a way of describing all separable subspaces. And this is called the standard Borel space of separable Banach spaces we are going to speak about. This will denote the isomorphism equivalence on SB, and these pointy brackets for X in SB will denote the equivalence class of X in this relation. All Banach spaces isomorphic to X. And the fundamental coding introduced by Bossard is just the quotient map from SB onto this quotient space. And now we can define, hopefully, what we call a Borel's family of Banach spaces. So a family which is, so it's a family in the quotient space up to isomorphism. A family is called Borel if the inverse image of G by this coding is Borel in SB for this standard Borel structure. And as well, we defined analytic families and co-analytic families. So a Borel set is a set, an element of the algebra. An analytic set, or sigma 1, 1 set, is a continuous image of a Borel set, or a projection of a Borel set. And a co-analytic set is a complement of an analytic set. Okay. Let's try to move forward. So historically, the first result by Bossard were the following. This equivalence relation is analytic in SB squared, meaning that all pairs of spaces that are linearly isomorphic is an analytic set which is non-Borel. So as a consequence, an easy consequence for a given X, the isomorphism class of X is analytic. And one big question is to determine if equivalence classes are analytic or even Borel. If they are truly analytic, that is analytic non-Borel or Borel. And the first easy example is little L2. Little L2 is Borel for some very simple reason. It's because of Kvapian characterization of spaces isomorphic to the Hilbert space, which is a space is isomorphic to little L2 if and only if it has cotype 2 and type 2. And if you think about it, having cotype 2 and type 2 is just a short sequence of countable quantifiers. Okay? And for this reason, this is Borel. And in fact, more generally, all local properties of Banach spaces are Borel properties. On the other hand, Bossard proves that C of delta, the equivalence class of C of delta, is non-Borel. It's a quite easy consequence of Milutin's theorem. So a C of K space is isomorphic to C of delta if K is metrizable, if and only if it is uncountable. And then you use the complexity of countable compact spaces to get the fact that this is non-Borel. So I'm not giving all details here, of course. The next result was open for a while, was to show that for P different from 2, the equivalence class of little LP is also Borel. And it's due to Godefroy, and it's a very elegant and very simple argument that I will describe here. The class of script LP spaces, a script LP space is either isomorphic to little LP or contains an isomorphic copy of little L2. And this is a local property, so this is Borel. And both of these conditions are analytic. This one we already spoke about, and this one it's because of the analyticity of the isomorphic relation. And there is a separation theorem by Suslin which says that two disjoint analytic sets can be separated by a Borel set. So there is a Borel set separating those two. Now you intersect this Borel with this one, and it gives you that this is Borel. The intersection of this one with script LP is Borel, so this is just this one. And the intersection with this one with script LP is also Borel. And that's the proof. So that's a very elegant argument. The next result is due to Gadir-Gavadra, which showed that for an Orlich function space, L phi, which is non-isomorphic to capital L2, then the equivalence class is non-Borel, which is a generalization of the fact that for P different from 2, the class of capital LP is non-Borel. And this is based on the complexity of complemented subspaces of capital LP. Okay. Well, I think I will stick to the mouse. So just a remark here. I will denote S of X, the set of all spaces that are isomorphic to a subspace of X. And again, it's a consequence of the first result that S of X is always analytic. And it's also an important question to know whether, oh shit. Okay, this brings me to one very important set of results due to Andrzej Kurka. One big question was to know whether the isomorphism class of C0 was Borel or not. And Kurka proved this in 2 steps. First, he proved that the set of subspaces of C0 is analytic non-Borel. And then in the second paper, he proved that the isomorphism class of C0 is non-Borel. And the main goal of this, of the first part of the talk, will be to extend the first line about the subspaces of C0. And no. Well, there is something at the end. If I can get there, because it's taking time. But yes, there is something at the end. Okay. Anyway, there are some very important questions. We still don't know if the equivalence class of little L1 is Borel or not. And there is a very good candidate for being Borel, which is little LP plus little L2, but this is still open. All right, just very quickly, you all know that we can also see any separable Banach space as a quotient of little L1. And this is another way of coding separable Banach spaces. So this is the formal presentation of this fact. And Bossard proved, so define the map from L1 to the power n into this quotient space, sending a sequence of L1 into the equivalence class of L1 quotiented by the linear span of Xn. And what Bossard proved was that testing that CD minus 1 is either Borel analytic or co-analytic, is the same as testing whether C minus 1 was with the first coding. So there are equivalent codings as long as you just want to know if the set is Borel or analytic. If you want to know about the Borel inside the Borel hierarchy, that's a different story. And I'm not going to speak about that. Okay, and then he also showed that this map sending a sequence to the closed linear, the orthogonal of its closed linear span is a Borel map, and the idea is that you can as well see a Banach space, identify a Banach space either as a closed subspace of C of delta, or the unit ball of a weak star closed subspace of little L infinity. And by doing that, you will get the same regularity. Okay. Now the properties that I will study in this setting are asymptotic properties of Banach spaces. The first definition is the definition of an asymptotically uniformly smooth norm, which is the following. A norm is PAUS, P asymptotically uniformly smooth, if for any x in the unit ball, any weakly null net, the limp sup of x plus tx alpha is less than 1 plus c times t to the power p. Okay, so it's like, of course, it makes sense only for p bigger than 1, and it's like better than the triangular inequality in some sense, but asymptotically. Okay, I'm not doing it the right way. Okay, more generally, what we call the modulus of asymptotic smoothness is the best constant such that you can have, maybe the pointer is working. This is the best constant such that you can have this inequality. And a space is called AUS without the P if this limit rho bar x of t over t is 0. Okay, just to give examples, a typical example of a PAUS Banach space is an LP sum of finite dimensional spaces. So this property doesn't care about the local properties. You can put any finite dimensional spaces in your LP sum, it will still be PAUS. I'll just make a picture here. If you have x, a given x the unit ball in your LP sum, and you take a weakly null net or a weakly null sequence, after a while it will be essentially supported after x, and the norms will add in an LP sum. So it will be PAUS. A C0 sum of finite dimensional spaces is called asymptotically uniformly flat, as Miguel mentioned, meaning that the modulus is 0 for t small enough. I'm really sorry. Okay, I really don't know what I can do. So I just take the advantage of this intermission to make a note in relation with Kurka's result. The set of subspaces of C0 is exactly the set of separable Banach spaces which have an equivalent asymptotically uniformly flat norm. This is what we proved with Godefroy and Kelton some time ago. Well, I keep going. Okay, so I presented the isometric properties of norms, and behind those properties, there are isomorphic properties, and they are related to weakly null trees. So let me introduce some notation. So for a set, this is a set of sequences of lengths at most n. And I use this one. Okay, thanks. Okay, so thank you very much. All right, I will still use a pointer, just to point. Now, this is a set of all finite sequences, and this is a set of infinite sequences. And as usual, this means putting the sequence T after S, the concatenation, and this is the beginning of S. And now, what we call a weakly null tree is a set indexed by, for instance, the set of all finite sequences, and a weak neighborhood basis of 0 in X. And we say that the tree is weakly null if you have this the following picture. So anytime you have a T on your tree, the set of successors is a weakly null net. And here, the weak neighborhood basis of 0 is directed by reverse inclusion. Okay? Okay, and now we have two definitions. We will say that a Banach space belongs to the class TP if there is a constant C such that for any infinite weakly null tree, one can find a branch of the tree such that along the branch you have an upper P estimate. Okay? And the class AP, which is smaller, is essentially the same except that there is a C such that for any n, for any height, and any tree of height n, there is a branch with upper P estimate. Okay? Please. So the first important theorem is due to Ryan Cozy, who proved that a Banach space belongs to the class TP if and only if it is PAUS renormable. And then, recently with Audrey, Fouvel, and Ryan, we closed the set of characterization of AP. A Banach space has AP. So look at condition 2i. If and only if there is a constant m, such that for any theta, there is a norm, which is m equivalent to the initial norm, and with modulus in power type P, but for T after theta. So that's the difference in quantification. And this is also equivalent to having what is called a summable Schlenk index. And I will quickly remind the definition of the Schlenk derivation. So if K in X star is weak star compact, you define S epsilon of k to be k, and you take off all V, weak star open, such that the diameter of V intersected with k is less than epsilon. So essentially what you do is you take off all those weak star open sets with small diameter. And having a Q summable Schlenk index means that there is a constant such that whenever you apply n times this derivation to the dual unit ball, and it is still not empty, then the sequence is not too big. The sum of the epsilon I to the q is finite, please. Okay, just a remark about the fact that AP and TP are actually different. I explained that T infinity is about subspaces of C0, and A infinity is what is called the class of asymptotic C0 spaces. And the typical example is T star, the Therelson space, which is actually reflexive. And in the case of P, you have to look at the dual of the Q convexification of T to have an element of AP and not in TP. So one corollary of this characterization is that this class is Borel. This is very easy because we are going to look at the coding coming from quotients of little L1. And the reason is that the Schlenk derivation is a Borel map on the set of closed subsets of the unit ball of L infinity with a weak star topology, and which is like an exercise. Okay, so the derivation is, this derivation is a Borel map, and it makes this class Borel. Okay, so next step is, you can go ahead, is now to find a universal space for the class TP. And this is essentially a result of Freeman, Odell, Schumprecht, and Zach. But it was not presented in those terms exactly, but it was really in the content of their papers. So there is a space in the class such that every space of the class is both isomorphic to a subspace and a quotient of UP. Yes, please. So a very quick overview of the strategy of the proof. The first tool is what I will call the P press-down norms on FDDs. So you assume that you have a space Z with an FDD H and a given P, and you define this quantity, this Z wedge P, as the infimum of GIZ and the sum little LP of the GIZ. So what do I mean by GIZ? I mean that if Z is the sum of the ZIs in C00 of H, then GIZ, and GI is an interval, GIZ is just the projection on the interval. Okay. Okay, and then this is not yet a norm. You use the next formula to define a norm, and what I will call Z wedge P of H is a completion of C00 of H under this norm. Yes, please. And the main feature of this construction is to force PAUS. Actually, it does better. It forces upper P estimates for points with disjoint consecutive supports in the FDD. So it's a strong version of PAUS. Okay. The next and main step of the proof in the paper I mentioned was to show that for any space in the class, you can find an FDD H such that X is a subspace of the wedge P of H. And you can find another FDD N such that it is a quotient of Y wedge P at J. Yes, please. Then once you have that, what you use is a kind of a universal FDD, which is due to Schechtman, which is complementarily universal for all spaces with FDDs. And next, last step, the universal step is actually W wedge P of J. And that's essentially the strategy of the proof. Yes, please. Just a very quick remark. You can do it for P infinity, but it's not the same universal space as C0. Because quotient of C0 are not the same as subspaces of C0. Okay. So what I'm going to try to prove now is that TP intersected with SP is analytic non-Borel. And I already mentioned at the beginning that Kurka proved that C0, the set of subspaces of C0, is analytic non-Borel. And we are going to extend this to P finite. Okay, please. So the first tool is the Q convexification, which is a very classical tool. Here is the formula for the Q convexification. You start with a Banach space with a one unconditional normalized basis, and X to the Q is a set of sequences such that this sequence here is in the space X. And then you define the norm of XQ to be this quantity. And this Q convexification has the property to be Q convex. It's just application of triangular inequality. Yes, please. And now if you look at this formula, and if you apply it with vectors with consecutive supports, you get this inequality. Because since they have consecutive supports, well, just think about it for 30 seconds and it's obvious, right? And this is actually showing you that XQ is QAUS. And as another consequence, you have that the canonical basis of XQ is shrinking. Okay. So if you assume, moreover, that En is boundedly complete, it's easy to see that it's also boundedly complete in XQ, and XQ is a reflexive Banach space. Now comes the key lemma. So assume that the starting space with a one unconditional basis is reflexive. Then little LQ cannot be isomorphic to a subspace of XQ. And this is classical. If you have little LQ in XQ, then you must have little L1 in X. So it cannot be reflexive. And the other part, maybe I will say a word on the board, is that the predual of XQ, so now we are in the situation where the basis is boundedly complete, so it has a predual. The predual cannot belong to TP. So let me try to explain this. So assume that this predual has TP. So then you can find, so what do I want to say? You can find Xn in the unit sphere of xq, you can find xn squared in the unit sphere of xq star. You may assume that they are with disjoint supports. And that this is biorthogonal. Maybe up to a constant, but not even because of unconditionality. Okay, once you have that, you may also assume, so recall that xq has tq. So xq has tq, so by taking a subsequence, you may assume that xn is dominated by the LQ basis. So remember the definition of TQ. The definition of TQ is whenever you take a point and a weakly null sequence, this is less than, and this is of norm 1. This is less than this. And if you iterate this estimate, you get that this is going to be dominated by the LQ basis. It's really easy. Okay, but if you assume that xq star has TP, this will be dominated by the LP basis. And then by Hölder's inequality, this one will be equivalent to the LQ basis. But this is not possible. Okay? All right, so next. I'm checking the time. You can give the whole page. All right, so as for a Courcas proof, what we are going to use is a family of spaces that has been built by Argyros and Deligiani in 1997, some Cyrelson-like spaces, which are the following. So K of 2 to the n is a set of compact sets of 2 to the n, and I is a set of infinite subsets of n. So what they built is the following family of spaces, Tm. They have a normalized one unconditional basis. If, that's funny, if they contain all three element sets, then un is shrinking. If m does not intersect I, then un is bundledly complete. So if you have both of them, this is reflexive. And on the other hand, if m intersects I, then there is a blocking of the basis, which is actually a C0 sum. Okay? So that's the family of spaces. And, well, again, give the whole page. Okay, so here is the idea of the construction. You look at A3, the set of all subsets of n of cardinality at most 3. And it's an easy exercise to see that it is a compact subset of 2 to the n. And you set xm to be Tm union with A3, just to make sure that all three elements are in the sets. So just because of that, the basis is one unconditional n shrinking. And the space will be reflexive if and only if the intersection with I is empty. Because that's when the basis is bundledly complete. And if not, remember, there is this C0 blocking, which is not reflexive. And to finish with this case, we have that if this intersection is empty, that Xm is reflexive. And by lemma 2, Zm, I didn't say what is Zm, so let me go back. So now Ym is a dual of Xm star, which has a boundedly complete basis. And so does Ymq, as we explained. And Zm, the Q convexification, and Zm is a predual of the Q convexification. So going back to the reflexive case, I just explained that this Zm cannot be in TP. Now, in this case, the fact that Xm had this C0 blocking will force Ymq to be an LQ sum of finite dimensional spaces. Okay, it's just an exercise on the definition of the Q convexification. But then, Zm will be a sum, an LP sum of finite dimensional spaces, and will belong to TP. So we have this dichotomy, either this condition and we are in TP, or this condition and we are not in TP. Okay, can you give the whole page? Even the consequences. Okay, and the end of the proof is now classical, and it was already used by Kurka. There is this fundamental result by Urevich, which proved that this set is analytic non-Borel. It's even what is called analytic complete, but I don't want to enter into that. Like any analytic set can be seen as the inverse image of one of these by a Borel map. Anyway, and again, what is not so easy next is to build a Borel map sending M to a space which is isometric to Zm. And once you're done with that, it's finished. You have proved that TP intersected with the separable TPs is analytic non-Borel. And so there are some consequences. I'm going back to your question. If you look at a dense sequence of finite dimensional spaces, and you call CP the LP sum of this sequence, then this class is analytic non-Borel. And I can give a word of explanation about that. So let me try to remember. If M intersected with I is empty, then our space Zm was not in TP. Okay, and obviously Zm plus CP cannot be isomorphic to CP, because CP is in TP. On the other hand, if M intersected with I is non-empty, what we have said is that Zm is isomorphic to an LP sum of finite dimensional spaces. So, in fact, Zm plus CP is isomorphic to CP. You're just adding more finite dimensional spaces. It's another sequence, another dense sequence of finite dimensional spaces. This is the same space. And the map, essentially the map sending M to Zm plus CP is Borel. Okay, and we can play the same game with our universal space and show for the same reason. It's a little bit more difficult, but for the same reason, this class is analytic non-Borel. Can you give the next page? Okay, so I will try to go quickly with the most difficult case, which is the situation of AP, and try to explain the difficulties. As I will say, there is no universal space for AP. But we can find some small families of universal sets. So here they are. You first define a Tyrrellson space with two parameters, the constant theta, which is here, and the sequence Mn, where the Tyrrellson condition depends. Okay? So that's the space T theta M. So this is kind of the implicitly defined norm, which can also be viewed as a limit of a sequence of norms. So the space is reflexive. It has a one unconditional basis. You can look at the Q convexification. It's reflexive. And as it turns out, the dual has AP. Okay, can you give me the next page? Then we have to do some press down again. So what I defined before was the LP press down norm. And I would use any vector of the basis here. Because the LP basis is spreading. Whatever subsequence you take, that's essentially the same norm. That's the same basic sequence. So here there is a small difference. We have to choose a vector of the basis. And we choose this one. And we define the press down or the wedge norm in the same way once we have defined this bracket. And one crucial step is to prove that if instead of little LP, you have a space with AP, then the wedge T of E also has AP. So this press down operation preserves the AP property of the space T. Okay, next page. And as you see, it will be very soon finished. Okay, the first result is the existence of these small families. So for any space in AP, which is separable, we can find theta Nm such that X is a subspace of, and this W of J is the Shechtman space, on which you do this TQM wedge operation. Okay, and this will be universal for containment, and you can find another one which is universal for quotients. And so we did not succeed to find a universal space, and there was a good reason for that, which is that there is none. And whenever you take a space which is in AP, you can find a theta which cannot be a subspace of a quotient of TQ theta n star. So in some sense, this is almost optimal. Okay, and thank you very much for your attention and for your help.
Could you go to the first slide? I mean those examples of, yeah, not that one. Further. Okay, here. No, the previous one, yes. So here we have two, concerning functions, continuous functions, we have two extreme cases, yes, like C0 and C over the uncountable metric compact space. What's the case of countable compact spaces?
That's a very
the densities.
That's a very good question. I believe it's open. And pretty sure it's open.
Okay, but what is your feeling for this case?
My feeling is that it's going to be analytic non-Borel.
Okay.
But if you take an isomorphism class which is like C of omega to the omega, I don't know the answer, but maybe there is a simple argument. I mean, it's possible. It's possible that you're right, but like at the moment, I don't see it. I would be surprised that Courcade did not mention it in his paper if it was easy.
Although there's some rigidity on the alpha spaces, so I don't know.
So yes, there are countably many different isomorphism class among the countable compacts, and there is one which is known. No, honestly, if Andrzej did not mention it, it must be open.
Thanks.
Now that you are on that slide, is there any universal space for which the class of isomorphisms is Borel?
The universal space for Hilbert spaces. Very universal. There is a result by Bossar on the Pelczynski space, but I think I don't want to say something stupid, but he may have proved that this is Borel or not. But I have to check. But there is a result about Pelczynski space that I have to check.
So, I mean, there are two examples we see, yeah, LOLP and orange. So what about the class of arrangement invariant spaces? Is there some class for which you can analog or orange?
Not that I know. So that's a really natural question, but after the work of Gadir Gavadra, I don't remember seeing anything in this direction. So
Or maybe some interpolation trick.
yes,
Indexing is probably
yeah, that's
possible to interpolate.
a good idea.
For inversion in the sense of Gilles.
Mm-hmm.
By the way, I like this. So you show this machinery for this Q convexification. So what about if you take this general instead of LQ, Banach Spaces values, this direct exclusion in the sense of E instead of LQ? I don't need to know. Yeah, I mean, direct size in the sense that you represent it, but instead of LQ, you take a Banach sequence values.
I see. So maybe what you would have in mind would be to find universal spaces for which the modulus has some given upper estimate. That's, again, a very natural idea, but never saw it anywhere. Yes. Yes. So one thing that has to be mentioned here is that if a space is AUS renormable, then it is PAUS renormable for some P. But your question is still valid anyway. It still makes sense.
can we find Banach spaces which are with isomorphic class Borel but of arbitrarily high complexity? Say, can you?
Okay, I'm not the right person to ask this. There has been two very important papers on this subject. One of the issues is that depending on the coding, you don't get exactly the same. So inside the Borel classification, the Borel hierarchy, you don't get exactly the same either G delta, F delta sigma, whatever. They can differ a bit. So there has been a paper by Godefroy and Saint-Remond about compatible topologies and giving some strong meaning to this classification. And a subsequent paper by Tsut, Duha, Dolezal, and I think there is somebody else that I'm forgetting at the moment. Kurka, yes, that must be him. Again, exactly on this topic. But I'm not very knowledgeable on this, but these are very interesting paper for your question, I guess.
Can you name the complexity of this?
Can I? Well, just write, there is a C, which is countable, such that for any x1, xn,
It's finite.
yes, so that's really two quantifiers.
Thank you for your talk. Do you know something about the class, for instance, of the Burari space of almost universal disposition, which can be described with few sentences, more or less like you said about Hilbert space and Papin's theorem? Maybe it's a stupid question.
No, certainly not. I just don't have the answer. No, I'm sorry. I don't see it. But no, I mean, everything is wide open, actually. Every natural space gives a natural question. And no, I don't have the answer, sorry.
Any other question? I stick to stupid questions. And L2 is Borel. The class of L2 is Borel. You know that they are twisted Hilbert spaces, right? And probably they're not Borel by far.
Probably.
Well,
probably, yes. Yes, probably.
I will. Then let's stand the speaker again, and a few minutes we'll start again with it.
Okay.
Ready?
Yeah, I
Okay.
hope so.
Gregor Plebanek is our last speaker this morning from Routledge University, who will talk about the title. I don't understand very well because it's complemented subspaces of spaces of continuous functions on a compact space, but in a compact space of a product of compact spaces or something. Anyway, it's up to you.
Yeah, thank you. I also would like to thank the organizers for organizing this nice meeting and for the invitation. I have prepared slides with many clicks, so now I'm very stressed. If I can go on. Let me just say first that this is I'm going to present a result obtained in collaboration with Jakub Rondosz and Damian Sobota, who are also present at this conference. They both are from Kurt Gödel Research Center in Vienna. And there is something unclear about the title. Okay, let us try to see if I can explain it. I will start by recalling the classical definition of a Grothendieck space. But first, the whole talk is about isomorphic structure of Banach spaces of continuous functions. So I assume always that KL, possibly with indices, will denote compact Hausdorff spaces. And of course, C of K is the usual Banach space of real valued function. Okay, and this classical definition of a Grothendieck property, it's the statement that you consider a Banach space X and you examine sequences in the dual, and every weak star converging sequence in the dual converges actually weakly in the stronger topology, then you say that X is a Grothendieck space, or it has the Grothendieck property. So if we if we just read the very definition in terms of C of K spaces, we can just state the following, that every sequence of measures giving functionals on the space of sign regular Borel measures with bounded variation mu n, if the sequence goes to 0 weak star, meaning those integrals disappear for every continuous function, then the sequence of measures should be convergent to 0 also on Borel sets. This is the just translation of the Grothendieck property, and perhaps I just wanted to state this in the zero-dimensional case, because then you will see that considering Grothendieck property for C of K spaces is so, say, measure theoretic in nature. Because if K is zero-dimensional, the meaning of Grothendieck property is the following, that whenever you take a sequence of nice measures, sign measures on K, and if the sequence converges to 0 on every closed and open set, then automatically it must converge on every Borel set. Okay, so this is what I'm going to work with the reformulation of the Grothendieck property for C of K spaces. So this is a classical fact. Usually it's difficult to find the reference for this, I think. Namely, the space of the form C of K is Grothendieck if and only if the space does not contain a complemented copy of C0. Okay. So, of course, we have classical examples of Grothendieck spaces. The first example, I think, is little L infinity. I will consider little L infinity in this form of C of K. So beta omega means here the Chexton compactification of the set of natural numbers with the discrete topology. This is Grothendieck, and somehow it's related to the classical fact that for instance, but I think this is Phillips' theorem, that C0, natural copy of C0, is not complemented in L infinity, but also you can prove that there is no way of putting C0 inside L infinity so that the image is complemented. And just to mention that, of course, this is, I think, the first result was proved by Grothendieck himself. But there are many generalizations of this fact. So typically, if you want to find some examples of C of K Grothendieck spaces, then you examine the algebra of Klopen sets. And if this algebra has some weak sequential completeness properties, I'm not going to mention them, then you can prove that C of K is Grothendieck. Many such properties were considered, for instance, in a paper by Koschmider and Schellach some years ago. And let me also mention that there is a very convenient survey paper by Gonzalez and Kania, published, I think, 3 years ago. This is a survey paper about various classes of Grothendieck spaces. Okay, but now now we're coming to the main point. Because on the other hand, you can, there are those results proved, I think, independently 40 years ago by Sembranos and Frenicke, that whenever you take infinite compact spaces K and L and you form a product and you consider continuous functions on the product, that such a space always contains a complemented copy of C0. So in particular, you can apply this result to the beta omega. So this space, which is perhaps surprising at first sight, is not Grothendieck. There is some way of putting C0 inside it in a complemented way. Okay, and now the result I'm going to present is, say, motivated by, for instance, paper by Alspach and Gallego, and they ask, can we find other separable infinite dimensional Banach spaces which can be contained in this C of beta omega times beta omega, and this image is complemented. I think they even conjectured that perhaps C0 is the only possible example of such a space. But it's not the case, because I'm going first to discuss our answer to this very concrete problem, and then later I will mention more general result. So that's why this is called corollary, because this will be consequence of our main result. Because we proved that this space continuous functions on the product of two copies of beta omega contains a complemented copy of, this is C over the Tikhonov cube of weight continuum. So quite a big space. But then from this you immediately conclude that our space contains a complemented copy, for instance, of C01. And also a complemented copy of C of L for every metrizable compactum. And in this context, I should mention that actually there are two cases if you consider metrizable compacta, because I think Milutin's theorem was already mentioned. So whenever L is metrizable but uncountable, that C of L is isomorphic to C01. This is this Milutin's theorem. And in the other case, when L is countable, there is this classification of isomorphic classification of C of L spaces due to Besaga-Pełczyński. And there are many pairwise non-isomorphic types of such spaces. And all of them you can put inside C of beta omega times beta omega, so that they are complemented. So this is more or less our answer to this problem by Alspach and Gallego. So let me go to our result stated in a more general form. So we just take a compact space K, and we don't need to assume that this is a product. We only need to assume that this K contains, say, a homeomorphic copy of a product of two compact spaces, K1, K2, and they say every of them is big topologically in the sense that it admits a continuous surjection onto the Tikhonov cube 0, 1 to power kappa. Then it happens that then C of K contains a complemented copy of continuous functions on this Tikhonov cube. So in the previous case, of course, you can just apply this fact that beta omega has this universal properties, so it can be mapped continuously onto every separable compact space, and 0, 1 to the power continuous separable. Okay, so this is, say, the main conclusion about the isomorphic structure of continuous functions on the product. But there's something I call here the main theorem, because this is actually the case we examine closely, we prove something, and everything else is just a conclusion. So let me give you the statement of this main theorem. We just consider the product space K1 times K2, where every K1 and K2 can be continuously mapped onto some compact topological group. And we prove, and in this case, we speak of isometric copy of C of J. This is this. So actually, this is the only result I'm going to advertise here. So I'm going to spend some time on the technology of this, which is behind this main theorem. Okay, so there are some ingredients. The first ingredient is a classical idea of Pełczyński of averaging operators. So let us consider two compacta, K and L, and some continuous surjection phi. Then, of course, you have in a very easy way you can produce from this isometric embedding of C of L into C of K. This is almost trivial, but the point is to examine when to give a sufficient condition under which this copy of C of L is complemented in C of K. And this condition, the sufficient condition, is so that we can somehow come back from L to K, not to points but to measures. So by P of K here, I denote the space of probability measures on a given space. So let me just draw a picture. So this idea is like this. We have one compact space, a surjection, which is called phi here. And think that this image is sort of thin. And then you embed C of L here by applying, using the composition with phi. And this is clear. So this sufficient conditions goes like this. Whenever you take a point here and you consider a pre-image of this point, so this is pre-image, you can put some probability measure here. It's called mu y. Mu y lives here on this pre-image. And then if you can do it in a continuous way, of course, I will equip P of K with the weak star topology. Then you have you know that this copy of C of L is complemented. Why? Because this is actually very easy to write. Because with this family of measures, you have this averaging operator defined here by integrating. And once you have this averaging operator, you can write the formula for the projection, which is given in the next line. And the main point is just if you apply this formula for T, for the function which is a composition of some continuous function with phi, you just get the value of, you just get G, because the measure mu y is a probability measure living only on the pre-image of y. Okay, so this is the first ingredient. And the second it's also starts with a very, very simple, well-known statement. Again, you have a continuous surjection between two compact spaces, and then if using this, you can define a surjection between the spaces of probability measures. So here, perhaps I will show you everything. Here, by phi of mu, I mean the image measure, which is defined below this block. Okay, so the first statement is well known that this is in the compact setting. If this phi is a surjection, then this phi also is a surjection between the spaces of probability measures. But what we need is something technical. Namely, for every measure in the target space L, on the target space L, we can find mu which goes onto this mu, but with the condition that, in a sense, it's a minimal example, in the sense that it has the same measurable sets, which is written here in the following way. Whenever you consider this sigma algebra of images of Borel sets in L, that the sigma algebra is dense in the sigma algebra of Borel sets on K. So again, this is very simple idea. For instance, imagine that you have a big space K, and this L is here, this thin L. And imagine you have some measure here. It's called nu. Or for instance, consider that just a projection from the unit square onto the first axis, and consider here, say, the Lebesgue measure. So there are many measures on the square that goes to this lambda, but what we need is something which is living, for instance, on this thin line, satisfying this condition. Okay, perhaps if I have time, I will comment on how you prove this theorem later, this proposition. But let me just present a very basic idea of this construction, and this is actually quite easy because we do start from the unit square. We start from the unit square. We consider the Lebesgue measure on both sides and the product measure, two-dimensional Lebesgue measure. And say this is, I'm going to name some sequence of measures on the square, and the mu0 is this lambda cross lambda. The first element of this mu1 will be just, you consider the product, the two-dimensional Lebesgue measure, but you restrict it to those two squares, and you normalize it. And you keep going like this. So, I mean, the next step you consider thinner squares, round diagonal, and your second measure is again the normalized restriction of the product measure on, to this smaller figure. So you can, I hope you can imagine what is mu3. You take thinner squares and keep going like this. So you approximate the diagonal with families of finite unions of squares like this. Okay, and this, so this is very specific sequence. It actually, using this, you can show that square does not give you a Grothendieck space because it's weak star converging, but not weakly. Also, perhaps let me start from the top, bottom. So this sequence of measures, it's converging to the Lebesgue measure, which is put on the diagonal. This is not surprising. But also, I decided to write here some technical observation because they are crucial. Namely, the basic property of those measures nu n is the following fact that every measure has the same marginal distribution. If you measure cylinders, horizontal or vertical cylinders, you always get the Lebesgue measure. This is easy to check. And from this, there is some observation I wanted to mention, but I need to explain the sense of this, of those calculations. Well, imagine that you understand how your sequence behaves on some class of rectangles. I call, for instance, you know what happens if you measure rectangles of the form A1 times A2. And then you want to conclude that the same happens for all the Bodel rectangles. And you can do it if, for instance, you can, using those sets A, you can approximate every Borel set up to some epsilon. Then there's a very simple calculations showing that this rectangle A1 times A2 approximates this rectangle B1 times B2 uniformly with respect to n, for all the n's. And this is calculated here. Okay, and then we come back to this basic idea. It was on the unit square, but we need to do something different. Okay, now imagine that this is we consider a compact group and its product with itself. You can just, the first thing you can do is just consider the circle. So rather than thinking of unit segment, you consider a circle, and so this G times G becomes a torus. So before, in this basic idea, I named some procedure of getting measure on the diagonal, which is the limit of some measures living on some squares. And now I want now to shift it. So imagine if this is a compact product group, I can shift diagonal here and there. So this, I mean, this red line is a shifted diagonal. And I can repeat this procedure of defining some measure on this shifted diagonal, which is the limit of product measures living on the squares in the same manner. And then you get, we get a measure which is called mu y, and we need to check what happens when we move this y here and back. So finally, what happens, we need to put all the things together. And for perhaps also I can show you what I'm going to discuss. Just for simplicity, I consider not arbitrary pair K1, K2, but consider 1K. But it's, okay, this is what I'm going to discuss. So now we imagine we have a compact space, and this is this product K cross K, and we know that this compact space can be mapped onto some, here this is compact group. So what we do, so on this side we consider the Haar measure, the probability Haar measure, and then we consider the product of lambda with itself. Here we have this, say, product mapping. And the first thing we do, we find a copy of lambda here. call it lambda prime. And by copy, I mean a measure which is a probability measure. It is transported to lambda under this mapping phi, but it has this density condition I mentioned before. And then what we actually do, we mimic this construction. We can perform this construction here. I mean, for instance, well, take some diagonal, and you know, using this approximation by squares, we are going to the limit. You define some measure living on this diagonal nu y. And we do the same construction here with respect to this measure lambda prime, and say the pre-image of this diagonal may be some more complicated set, which is on the set we have this measure mu y. And this is more or less the main trick, namely we have a so the final mapping, look at it's written here, I call it theta. There is finally we consider the mapping from the product K by itself into G times G, which is we apply this group operation, it's minus. So the coset of this operation are those shifted diagonals. So by this construction, we know that this theta is giving us a complemented copy of CG, because we have this mapping in the Pełczyński style, which is weak star continuous, and those measures mu y live on the pre-images of G. Okay. Okay. This is just as a formulation of the main say result, because you may wonder how you can detect that your given compact space K contains a product of two, say, big compact spaces. And it's perhaps good to write it using the typical duality between zero-dimensional compact spaces and Boolean algebras. So this can be transmitted to the statement that, for instance, consider some zero-dimensional compact space, and it's algebra of Klopen sets. And if you can check that this Boolean algebra admits a Boolean homomorphism onto a free product of two non-atomic Boolean algebras, then this gives you inside K, this gives you a non-trivial product of two compacta, and then you can conclude from the main result that C of K contains a complemented copy, say, of C01. And in this context, I would like to mention something which is perhaps quite well known, interesting non-metrizable compact space, which is the double arrow space. You just consider two copies of 0, 1, and you split every point into two, and this is you define, you consider lexicographic order, and this lexicographic order defines a topology on K, which is compact, so you get something which is now called compact line. And this is, I think this is well known, that if you from this double arrow space, you have a natural projection onto the first coordinate, and it's continuous, but it gives a copy of C01 inside C of K, which is not complemented. And even more, I found a result which is more general in a paper by Andrzej Kalenda and Wiesław Kubiś, that actually this copy of C01 cannot be enlarged to a separable subspace which would be complemented in C of k. So somehow, so then we didn't know what happens with copies of C01, complemented copy of C01 inside C of this k, but it's actually, it's using completely different method. It was proved by Marciszewski years ago that you can put C01 inside C of k in this complemented way. So just, I mentioned this because this is the example where our, say, corollary does not apply. Because this double arrow space, it's a line. It's, you know, it cannot contain, this is intuition, it cannot contain a product, which is actually true. It's not actually our discovery, but I think that this fact is due to Sabine Koppelberg in the language of Boolean algebras. But I wanted to mention that it's really the case that some years ago with Gonzalo Martinez Cervantes, we had some result, and we gave a notion of some kind of a dimension. And here you can apply it here to check that say the dimension of this double arrow space is 1 because it's a compact line, while every non-trivial product of two compacta is of dimension at least 2. Okay. Any problems? Always we have some problems. So this is not very well formal, but somehow the previous considerations suggest that we can ask: is there a nice way of characterizing compacta, okay, such that C of k contains a complemented copy of C01? I mean something practical that might be used to check some cases, say in the language of topology of k. And there is also a natural question. Sorry, it was too fast. So I mentioned beta omega can be mapped continuously onto every separable compact space. But we couldn't answer this problem. Can we take any separable compact k and put it C of k inside this continuous functions on the product so that it becomes complemented? There are also, now I recall there's another question. I think Damian suggested this. It's sort of technical. In this construction, we used some measures. They were those measures mu y. They were non-atomic. And now you can ask the question: can you say demonstrate that the space C beta omega times beta omega contains a complemented copy of C01 using only atomic measures? And this is, at first sight, this is just a technical question, but it has some meaning, because you can also, with C of k spaces, you can consider wicked topology, this topology of pointwise convergence, and you can always ask what happens. You can define the fact that the subspace is complemented in this topology, and we don't know what happens here. Okay, and then let me just comment on this measure theoretic tool, which I think was the main ingredient. So again, you consider a continuous surjection. On the target space, you have a measure, probability measure, and I stated the fact that you can find the measure mu, which is transmitted to this given measure nu, in some very specific way, so that this sigma algebra sigma is dense with respect to this measure. Let me just mention, because there's a very easy proof of this. First of all, there's easy proof that you have measures mu which are transmitted onto nu. This is just a version of Hahn-Banach theorem. And going in this direction, once you know that the set, it's called here M, it's non-empty, you discover that this is a closed and convex subset of in a compact space P of K, so it has extreme points. And every extreme point has this property that the sigma algebra sigma is dense. But somehow, it's sometimes psychologically better to have a more natural approach to this kind of result, because if you want to define this measure mu, the first step what you do is to define. I should perhaps write this. You have some measure nu here, and you have a continuous surjection phi, and you want to define this measure mu. So the first step you do, you of course define that mu of the pre-image of any Borel set in L must be what it should be, it's mu of A. So this is, the first step is obvious. So this is the, in other words, you can define this measure mu on this, by the formula on the sigma algebra, sigma. The only question is that in general case, this measure is, this domain is not much smaller than all the Borel sets, so you need to extend this measure somehow, and there is some extension procedure. And this is again kind of a Hahn-Banach theorem, but for the measure theory. You add closed sets, new closed sets one by one, you extend it by some formula, and use transfinite induction. So all this, what I'm saying, of course you can say, when we prove Hahn-Banach theorem, we do the same. We add vectors one by one and use transfinite induction. But here, if you have this, see this procedure, you can easily control additional properties of this measurement. My impression is that this was the last slide. I forgot to write thanks for the audience for listening. So that's all. Thank you.
Are there comments? Remarks?
So in the case of Banach lattices, this is known that Banach lattice has a Grothendieck even only if there is no surjection on C0. Yeah?
Surjection.
Surjection.
Okay.
On little C0. So, I mean, what about this idea of your nice proofs about the question to have a surjection instead of projection for these problems you discuss?
So you're asking how the property that given Banach,
for this product of these compacts like LUGAR,
I think this is the same, because if you start, well, for instance, if we want to characterize Grothendieck property, I don't think about lattices, but about Banach spaces of the form C of K, right? So actually, this fact I mentioned before, that C of K, say, is not Grothendieck if and only if you have this non-trivial converging sequence of measures. And then I think it's immediately give you a surjection of C of K onto C0, if you start with this. Okay, so you're asking, can I translate these main results? Say, no, I need to think about this, but it's a nice suggestion.
Any other questions, comment? I have one thing to say. Can you please come back to some place where appears continuous on beta n times beta n? Any place?
No. Coming back is this direction.
Yeah.
Back.
Any place where it appears continuous functions on beta n plus beta n. Well,
Okay. So let us come back to the beginning. This was the first corollary. Okay, it will be here.
Yeah,
Yes.
there. Yeah, on L infinity, you said, well, it contains the natural copy of C0 is not complemented. So all copies of C0 are placed in the same position in L infinity, so one is not complemented, no one is complemented. But the point is, I don't know if this is true for beta m times beta n, but the point of this wonderful thing you proved here is that if continuous functions of beta n times beta n contain C01 complemented,
And uncomplemented. You mean?
Uncomplemented, then that space is not separable injective. And this is something that the only thing I knew was a proof of Peter Scholz, who was able to prove that the space is not separable injective. So this is another proof.
Yeah, I think so. Yeah. Because of course you can easily put C01 in an uncomplemented way.
Yeah.
Because you can just do it. It's into C of beta omega, and which is subspace of C of this product.
Yeah.
So yeah.
I guess that even in the lecture notes of separable injective, we put that on as a problem. If this space was separable injective or what?
But sorry, so say it again. So you mentioned this
space.
result that
Continuous functions on beta omega times beta omega is not
separably
injective.
injective.
That I think we put as a problem in the lecture notes. I only knew a proof of Peter Scholz, who proved that was not separably injective.
I see.
So this is another one.
Okay, thank you for the suggestion.
That and many other spaces with the same technique. I mean, once a space contains C01 complemented, cannot be separably injective. Right? Okay, let's turn the speaker again.